In the late 1990s, Dubai was expanding rapidly, fueled largely by its oil reserves. But those oil reserves came with a hard expiration date, projected to run completely dry within just a few decades. To ensure its long-term survival, the nation's leadership made a massive pivot. They decided to transform the region into a global hub for luxury tourism. That ambition ran into an immediate geographical problem. Dubai only had 72 kilometers of natural, usable coastline along the Persian Gulf. For a global beach destination, that simply wasn't enough room. Developers initially pitched a straightforward solution: dredge up sand and build a simple, circular artificial island off the coast. This would add about 7 kilometers of new beach. Sheikh Mohammed bin Rashid Al Maktoum rejected the circle. This animated diagram shows exactly why. By stretching the landmass into a fractal-like palm tree with a central trunk and 17 distinct fronds, you mathematically maximize the perimeter. The design pushed that 7 kilometers of new beach up to 70 kilometers. There was a strict material constraint attached to this design. To ensure the island blended with the marine environment, the foundation couldn't use concrete or steel, only natural sand and rock. Securing Dubai's economic future required forcing a massive, entirely unnatural structure into the turbulent waters of the Arabian Gulf. The first step was protecting the delicate sand that would eventually make up the palm fronds. Engineers had to build an 11-kilometer crescent breakwater out in the open ocean to absorb the Gulf's waves. Constructing this barrier required a continuous fleet of barges and haul trucks, dropping 7 million tons of blasted rock onto the seabed day and night. The massive wall did its job. It effectively blocked the kinetic energy of the ocean waves, creating a calm, protected zone inside the curve. This diagram illustrates a critical failure. The continuous wall worked too well. By blocking natural tidal flushing, water trapped inside the crescent quickly stagnated. To fix this, crews cut 2 massive gaps, each 100 meters wide, through the rock, allowing fresh seawater to circulate. Mastering the coastal environment meant engineers couldn't simply block the ocean's power. They had to negotiate with its tidal mechanics to prevent the internal water from turning into a dead zone. With the breakwater secured, the team moved to the next phase, depositing 94 million cubic meters of sand to build the actual fronds. Standard dumping methods were useless here. Pouring sand from a barge couldn't possibly create the highly specific, intricate shapes required for the 17 distinct leaves. Instead, they used a technique called rainbowing. Specialized dredging ships vacuumed sand from the seafloor, then blasted it through the air at 10 meters per second, spraying it precisely into place. To hit exact coordinates in the open water, the ships relied on an orbital guidance system, using high-tech GPS and satellite imagery to map the ocean floor in real time. The process also required a physical human check. Every day, a team of 5 surveyors walked the newly sprayed sand edges, carrying GPS backpacks, verifying the satellite coordinates on foot. Building the island was a surgical operation, guided from space. But the newly built landmass had a fatal structural flaw. Loose ocean sand cannot support the immense weight of concrete infrastructure and skyscrapers without shifting. Furthermore, the region's proximity to an active earthquake zone meant that any seismic stress could cause the loose sand to turn to liquid, a process known as liquefaction. The solution was a process called vibrocompaction. A large metal probe is driven deep into the ground, where it violently vibrates, forcing the scattered grains to instantly lock together. Operating at a staggering scale, 15 specialized machines continuously drilled 200,000 holes across the entire island for 8 straight months. The combination of these severe vibrations and high-pressure water injection forced the individual sand particles to permanently interlock, forming a highly dense matrix. Vibrocompaction took an unstable pile of sand in the ocean and upgraded it into a rigid, viable foundation capable of holding a city. Today, that raw, compacted sand has been completely covered by the finished reality of the mega project. The island now supports 80,000 residents living in apartment complexes along the main trunk, alongside 1,500 private beachfront villas lining the fronds. This density is enabled by hidden infrastructure, including a network of subterranean vehicular tunnels, operating at depths of up to 25 meters beneath the ocean surface to connect the outer crescent to the mainland. The luxury tourism strategy paid off. The outer ring houses massive resorts like Atlantis, the sprawling Aquaventure water park, and a central marina capable of docking 800 yachts. Visitors can observe the entire layout from the view at the Palm, a 360-degree observation deck suspended 240 meters in the sky on the 52nd floor of the Palm Tower. Dubai must continuously spend millions on environmental mitigation to manage coastal erosion. But the Palm Jumeirah stands as proof that with enough engineering precision, humanity can literally redraw the map of the world.